Welcome. Today we're going to be looking at lesson 6.4, discovering the graphs of polar equations. And folks, they make some beautiful pictures, so it'll be fun today. What I'd like to have you do is get your graphing calculator set up first. I'm going to ask you to make sure that you get into degree mode is how I have mine set. Also, I've made a change on the function line right here. Instead of being in function, I want to be in polar. So if you would make those two changes, that's under the mode key. Then I would ask you to go to your window. We're going to set up a window that we can graph these things through. The window looks different in polar form. That's because you have to account for circular motion. So theta min, the smallest angle we want is 0. The largest angle we want is 360, as in we're going to go one full turn, if you will. We're going to step by 15 degrees, which is a 12th, I think, of 360. Then I want you to set your x min at -8, x max at 8, and x scale 1. And y's, I'm going to ask you to do the same thing, -8 to 8 by 1. Okay? See, I want you to hit your zoom key, and I want you to zoom square because we want to see these things in the right perspective. And I don't have anyone showing yet, which is okay. All right, so we should have our blank screen up there. And then we're going to talk first about this type of equation. In these type of polar equations, the graphs are circles. They have the format, some multiplier times the cosine or sine of theta. This one is the cosine, and I'm wondering if you can tell why. Here's the sine one. Remember how we've always said that x goes with cosine? And notice that this is across the x-axis. Y goes with sine, and this is across the y-axis. I have one of these in my y equals that I'd like to show you right now. I have several graphs in there, but I want to only use them one at a time. I put in -3 cosine theta. The negative, what do you suppose will be the result of that? Let's take a look and see. Instead of being on the positive side of the x-axis, we're over here on the negative. And notice that the diameter of that circle is 3. Okay? There you go. The next type of graph that we're going to look at, these equations have this format, constant plus multiplier sine or cosine theta, and you could have plus or minus, so there are lots of variation. These have a cool name. They are called limasones. L-I-M-A, and then it's a C with that little accent under it, limacone. They look kind of like circles, but look at that one, got a cute little loop in there, and this one's just kind of got a dimple, if you will. This one also goes in, but it's not as pronounced as this, and this one has kind of a flat spot on it. All of those arrangements come from the relationship or the ratio between the A number, the constant, and the B number, which is the multiplier. I have one of these in my y equals as well, so I'm going to shut my first graph off and come down to the second. I have in here 5 minus 5 sine theta. 5 minus 5 sine theta. So I'm following this pattern. The ratio between my A and B is 1, 5 to 5. So I should get a graph that looks like this one. Let's see if that's what we get. Yep, can't see the bottom of mine because my window is not deep enough, but I'm happy that I got the top to be right. So limacone. Okay. The third type of equation that we're going to look at, these are called rose petals for obvious reasons. And the format for these equations are multiplier sine multiplier theta, right? Or multiplier sine or cosine multiplier theta. The one that we're looking at here is a sine wave. It has 1, 2, 3, 4, 5, 6, 7, 8 petals. The equation for this particular one would be, what's the radius on it? 2. See, it's going out to the second ring there. So 2 sine, And if n is even, the n, the multiplier here, you get twice that number of petals. So for us to get 8 petals, this must have been a 4. 2 sine 4 theta. If n is odd, you'll get n petals. So you will find out A gives the height of a petal, if you will, okay, the distance between the origin and the tip. If you think about that for just 1 minute, if n is even, there'll be 2 n petals. So if I wanted to get 2 petals, I'd be stuck, folks, because 1 won't do it. 1 is an odd number, but you'd get 1 petal, which would be kind of silly. If you put an n of 2 in there, you're going to get 4 petals. So there are some even numbers that you cannot get, okay, which is kind of interesting. Let's look at this one in the y equals. This is my third equation there. So I am going to be looking at 5 sine 4 theta. The 5 tells me I should get the height of a petal is 5. I have 4 as the multiplier, which is an even number, so I should get 8 petals. Actually, that should look like this, only with longer petals. Let's look at that. Yeah, there they are. 1, 2, 3, 4, 5, 6, 7, 8. And you'll notice that the axes here go between the petals. If you put a cosine in this one, then the petals go through the axis, or else, as you could, it would be like that. It would go through them. We have 2 more to look at. The next, these guys' equations look more complicated, and they are. R squared equals a squared sine twice theta, or a squared cosine twice theta. These guys are called lemniscates. Lemniscates. And I have programmed them into my calculator, one of them. We need to talk about the way that you graph this. This type graph, the lemniscates, need to be graphed in 2 stages, folks, because you can not graph r squared, you can graph r. So you graph it once with the positive square root and once with the negative square root. If you look at mine, I have a 16 in here, and that is the square of 4. That means that the length, or again the height of one of these ends is going to be 4 for mine. Let's take a look at this one in the coordinate plane. This is a sine that I have going, and the sine ones have to do with the y-axis, so I want you to see where they come out. The sine one is the one that's tipped like this. Cosine lays flat along the x-axis. So the last type of graph we're going to talk about today have equations in this format. R equals multiplier times theta. Those are called spirals of Archimedes. And they create a spiral. Pretty cool. Spirals of Archimedes. I have one in my y equals. I've made my multiplier 1/10, and in the window that I'm viewing, we're not going to be able to see much of it, but I'm going to go ahead and hit graph. And there's the start of it. Let's just do this. I usually don't do it, but let's zoom out a couple times. Zoom in 3, then you hit enter, and it will zoom out about where the cursor is. There you can see. So you can see as theta goes from 0 to 360, we get well, I have 1/10 of that value. So a nice little spiral here, and it stops here because we're only looking at the first full turn. If we increase the theta max to 720, we'd go farther. But anyway, pretty cool idea. So 1, 2, 3, 4, 5 types of polar graphs that we're going to be looking at. We'll have fun working with these and exploring them a little bit more in school tomorrow. Don't forget to try that. You try.